Hello and welcome to our video series on high-end GNSS testing with the Rohde and Schwarz SMW200A. In this episode we are going to have a look on coexistence simulations for GNSS receivers. This kind of testing is necessary to assure that a GNSS receiver works reliable in an environment where multiple other radio signals are present. Special care has to be taken when the GNSS receiver is integrated in one device with other transceivers. For example, a GNSS receiver in a smartphone is operated in the direct vicinity of transceivers in the GSM, Edge, UTMS and LTE bands. These transceivers transmit with high power and might couple to the GNSS receiver. Also, mixing products and harmonics of these cellular signals fall directly into the GNSS L1 band. In this video, I want to give an example on how to perform a co-simulation of GNSS and other radio signals. All we need for this is the Rohde and Schwarz SMW200A GNSS simulator. So let's get started. Here you see the simulation setup we want to configure now. Besides the GPS, GLONASS and Galileo signals, we simulate an interfering radar signal and a coexisting LTE signal. First, I'll put the SMW into an advanced operation mode to allow the co-simulation of multiple digital standards. As you see, we have 4 basebands available to configure GNSS in combination with other coexisting signals. Additionally, we have 4 internal noise generators to configure additional interference sources as shown in the previous episode. I configure a combined GPS, GLONASS and Galileo L1 E1 signal with default settings in baseband A. As we want to perform a multi-frequency simulation, I configure the corresponding L2 signals in baseband B. A potential source of interference is the downlink of LTE band 24, which is located in the frequency range from 1525 MHz to 1559 MHz, close to the L1 band. To test that the receiver can handle the presence of the signal, I set it up in baseband C. As the 4 basebands are routed to only 2 RF ports, the different carrier frequencies are realized with the frequency offset in the baseband. And I also set the power of the LTE signal via offset in the baseband. In baseband D, I use the arbitrary waveform generator to play a pulsed signal which is typical for long-range radars operating in the frequency range from 1215 to 1240 MHz. The radar signals interfere with GNSS signals provided on L2. Again, we use a frequency and level offset in the baseband to obtain the correct RF radar signal. Finally, I configure the correct routing. Thanks to the full flexibility of the stream mapper, I can assign the basebands to the RF outputs in any variation or combination. For our simulation, basebands A and C are added and routed to RF port A. The basebands B and D are also combined and routed to RF port B. So far, we have configured this scenario. It contains the L1 and L2 GNSS signals, the LTE signal, and the radar signal. Now, the AWGN blocks can be used to add even more interference sources like AWGN or CW interferers to your simulation. How this works has been shown in the previous episode. The simulation scenario with 6 interferers looks like this. In each of the frequency bands L1 and L2, a CW interferer and AWGN is added on top of the modulated interferers. RF port A and B need to be connected to an external combiner, and the resulting signal is fed to the DUT. This concludes our episode. You have seen how to set up a multi-frequency GNSS simulation in the advanced mode of the SMW200A, how to co-simulate other digital standards, and how to use the ARP to add arbitrary signals to the simulation. This way, a GNSS simulation with 2 coexisting interferers has been set up. When we are additionally using the AWGN blocks, up to 6 interferers can be generated out of one single box. Check out our other application videos, where we show more of the SMW's capabilities for high-end GNSS testing. Thank you for watching and see you next time.